Hello, calculus students. This lesson is going to be over concavity. We're going to be using the second derivative to test for concavity. Basically what concavity is it's pretty much what you would think it is. For example, on this graph, this part here that I'm tracing around is concave downward, okay? And this part here is concave upward. So when you're testing for concavity, you're going to use the second derivative, okay, instead of the first derivative like we did for relative max and mins. And it's going to be, if the second derivative is greater than 0, then we have a concave upward situation on the interval. If it's less than 0, then we have a concave downward in that interval. And the point of inflection is where concavity changes. So in here, this would be the point where the concavity changes, right here. So that would be a point of inflection right there. To find the point of inflections, similar to how we found the relative max and mins, or our critical numbers, was to set the to find the critical numbers, we set the first derivative to 0, or where it was undefined. Here our points of inflection are going to be what the second derivative, when the second derivative is 0, or where it's not differentiable. Okay, so we're going to do an example here. So when we're testing for concavity, we need to find the second derivative, which can be kind of a pain in the rear end sometimes if you have a complicated function. So this function right here, we'd have to use the quotient rule to find the first derivative, which I did, which is right here. Okay, there's the first derivative. And then we use the quotient rule again to find the second derivative. And this gets very complicated, so if you're having some trouble simplifying this, let your calculator help you. Your calculator can help you find the derivative or simplify. You can type this in and your calculator will actually simplify for you to get to here, okay? So don't spend so much time simplifying, just let your calculator do some work for you. Okay, so we're going to have to find the points of inflection. So the points of inflection are going to happen when the second derivative equals 0. It's one situation. So we have to set the numerator equal to 0. So 36, sorry, this isn't working very well. Okay, so I set the numerator equal to 0 and factored this. So x can either be 1 or negative 1. Also, I need to look at the denominator and make sure that the denominator cannot be 0, because that's where the second derivative would be undefined, which would also be a point of inflection. But because we're squaring 2, so no matter what x is, it's always going to be positive. The denominator here is always going to be positive. So there's nothing, no points of interest down there. So we're pretty much stuck with these intervals. I've taken my points of inflection and I've put them up here in my intervals. Okay, so I'm going from negative infinity to negative 1, from negative 1 to 1, and from 1 to infinity. I put my test values here, just like we did before when we were talking about possible relative max and mins. So we're going to find the sign on the second derivative. So if I take a negative 2 and I plug it in here, I'm going to square the negative 2. The denominator is always going to be positive. So if I square the negative 2, I'm still going to get a positive 4. Subtract 1, that's still going to be positive. So when I multiply by 36, that's positive. When I plug in 0, squaring 0 minus 1, I'm going to have a negative 1 times 36. So that sign is going to be negative. And then for 2, when I plug in 2, that is also going to be positive, my second derivative. Okay, so I'm plugging these numbers into my second derivative. So the conclusion is, since my second derivative is positive on this interval, the graph is going to be concave up. And between negative 1 and 1, this is going to be concave down. And between 1 and infinity, that's going to be concave up. So my two intervals for concave up are between negative infinity and negative 1, and 1 to infinity, concave up, and between negative 1 and 1, this is concave down. Okay, so now I want you to give this a try. Okay, you're going to first find the second derivative of this, and this is a little bit easier. Then you're going to set your second derivative equal to 0 to find out your points of inflection. The points of inflection are going to help give you your intervals. Pick a test value, find the sign, and draw your conclusion. Okay, go ahead and give it a try. Okay, so the first derivative of this, let's get red here, is going to be 4 times x to the third minus 12x squared. Then we have to find the second derivative, which is going to be 12x squared minus 24x. So hopefully you got that far. Then you need to figure out where your points of inflection are. So you're going to set this equal to 0. And we could factor out a 12 and an x. And we would have x minus 2. So x can be 0 or 2. So those would be our points of inflection. So our intervals would be negative infinity to 0, 0 to 2, and then 2 to infinity. We need to pick our test values. Pick negative 1, 1, and 3. Okay, always pick easy numbers. I'm going to test these values in our second derivative. So if I plug in a negative 1 in here, okay, I would square my negative 1 and get 12. And then 24 times a negative 1 is going to be negative, but a minus a negative is going to be positive. So this is going to have a positive sign. When I plug 1 in here, I'm going to square 1, I'll get 12, minus 24. So this is going to be negative. When I put 3 in here, I'm squaring 3, that's 9. 9 times 12 is a bigger number than 24 times 3. So this is going to be positive again. Okay, so if this is positive, that means concave up in this interval, concave down in this interval, and concave up from 2 to infinity. Okay, hopefully you got that answer, and I'll be able to try some of these on your own.